Well, so I was scrolling Reddit the other day and I came across this post called Will Smith Eating Spaghetti, right? So we have what it looked like in March 2023, which is actually not that long ago. And you can see sort of it somewhat looks like Will Smith eating spaghetti, but you wouldn't say that's very high fidelity, right? But now compare it to what we can do now with Google VO3, and this is what Will Smith now looks like eating spaghetti. To me, I can't tell fact from fiction anymore. And so it sort of inspired me to start talking about how these models work and how we got from there to what we can generate now. We've used these video generators a little bit in another video, MikeBot.
Hi everyone, I am MikeBot.
That relied heavily on the video generation part. So I thought let's talk about how these work. Now, they work very similar to how 2D images are generated. If you remember, Mike has done a fantastic video on that. But to really understand video generators, I have to sort of go over a quick recap of what happened in the last video, right? So how these models are trained, and this all uses something called diffusion, is you'll have a data set, and let's say you have an image of a frog, right? And what you do is you start adding noise to this image, right? So what this frog now looks like is a frog with a little bit of noise there. And when I say noise, I'm talking like back in the day when you had those old TVs, and you had to change the aerial to get them, that sort of noise, right? T equals 2, and then eventually you just get to pure noise. So you can no longer tell that that's a frog, right? So you have, and let's say that's T equals 20. These are the time steps, right? So how do we train one of these models? So let's say you have the ground truth image for reference here. And then you'll pick, let's say, this one here, let's say T equals 2. And you'll have your diffusion model here. You say to the diffusion model, you go, right, what noise have I added here to get this image, right? What noise do I need to take away from this image to get this nice, clear image here? And the neural network goes, okay, here we go. So you need to take away that amount of noise, right? And so what you do is you then take this noise, you then subtract it from that, and what you should get is something like this, right? In reality, you probably won't get exactly that, but you'll get something like that. And then what you do is you compare the subtracted noise of that compared to this, and then that's your loss, and then you can update the diffusion model. And what happens is that this diffusion model gets very, very good at accepting an image with lots of noise in it and predicting what the noise should be based on a prompt. And so the prompt would be, in this one would just be frog, and your time step as well. And so when you say frog, it knows to generate noise that when taken away from that image will end up giving you a frog. And then what that means is that you can combine different concepts, right? So I've realized I've run out of space already. So let's say now you want to generate, and this is with a fully trained diffusion model, you want to generate an image of some frogs on stilts. You give the neural network an image of some noise. And then what you do is repeatedly ask the neural network, okay, what noise do I need to take away from that to give me some frogs on stilts? And the neural network goes, okay, you need to take away this noise. And so what you do is take away that noise from that noise. And then what happens is you'll start to get maybe a bit of an outline of something like this, but it's mostly just noise, right? And what you do is you repeat this over and over and over again for, let's say, 20 steps. And then eventually, what you'll end up getting is an image of some frogs on some stilts. I'm not sure if you can tell it's a frog on some stilts. It's got slightly longer legs than the other one, but that's meant to be a frog on stilts, right? And so basically, this diffusion model has learned all these different concepts, and now it's able to combine them to generate something very abstract like a frog. You'll never see a frog on a stilt, but it's able to generate it, right? And that's all done via predicting noise and taking it away from the image. So that's a whistle-stop tour of how 2D diffusion works. I say if you're still a bit lost, I recommend going and watching Mike's video now before we move on to video generators. So I think before we talk about video generators, we should talk about how a video is stored or represented in a computer, right? So a video, realistically, is just a series of images, right? So what you're watching here isn't a continuous signal of me. It's me sliced up into many, many images at something like 30 frames per second. Is that the sort of
50 at this point.
50 frames per second, right? So that's 50 images of me per second, and when you view it, it looks seamless, right? There isn't any jitter of me. What we're doing now is we're going to diffuse over many, many images to create a video, right? And actually, these video generators work very similarly to the 2D one, but as I say, you're now working with videos rather than just a single image, right?
Can I ask a question then?
Yeah.
So I know from my work with video and animations that if you make a slight change, if you go too far in a change between one, what we call frame, and the next, it can look a bit odd.
Yes, jittery.
Presumably that's the big problem we've got to fix here, isn't it?
Indeed, yes, we've got to make it seamless, right? Smooth, yeah. And when you're talking like, if you VO3, which is going to be the big model that we'll show at the end, that's generating at 24 frames per second over 8 seconds, right? So that's a lot of frames that it's got to work with, and it's got to have continuous movement and smoothness. You may be asking, okay, what if we just use, let's say, the 2D diffusion network to try and generate a video? So you have all these frames. This is why I'm not an artist. If you put them through your diffusion network, and of course you do over many, many time steps as well, what you end up getting, and this is with the caption, frogs on stilts, sensing a theme here. This will be what we're using for the video. And you do this for everyone as well, pass that in, as well as your time step, T as well. Anyway, what you'll get is you'll get like one frog up here, all nice and happy, but then you'll get another frog, let's say, and his stilts are coming over here, and he's green, and this one's blue, you know, and you may get one with multiple frogs in it, because every time you use the neural network, the diffusion model, it does not know what it's generated before, right? And I've tried, let's say, doing, if you have 20 time step, on the 19th one, using the same noise and adding a bit of noise to each of that and generating it. What you get is like variations of the same image, and it's not going to work, right? We need the diffusion model needs to know every single frame it's generated, so that it can generate one smooth, continuous video, right? Like Will Smith eating spaghetti, right? So basically, we need an upgrade. We need a big upgrade here. So let's upgrade this now. So let's say, I'll go into the specifics of the model in a second, but essentially what we do now is when you train it, you now are training on videos, right? And so let's say, for the sake of argument, it's 4 frames of a video. It won't be 4 frames when you train on this. It'll be many, many frames, but let's say 4 so I can show you this properly. So you have a video, and the caption is a frog jumping. So notice how these text captions now have movement as part of it, right? Also, you can have movement in an image, but it will capture a frog mid-jump or something like that. Now, we actually want the frog jumping, so you need to have, you know, a description of the movement that you want in the video. So let's now draw a frog jumping. So also, don't ask why my frog has legs like that. I don't know either.
Frog's legs.
Frog legs, yeah, there you go. So you've got a frog, it's jumped up in the air, now it's landed, right? As I say, this will be over many frames. So what you do now to train it is you would start adding noise, just like the 2D one. Now, I'm not going to lie, Sean, you're probably going to have to cut here because I'm going to have to draw all this out again with noise. We've now added noise to each of these frames over a series of time steps. Right? I've tried to draw it here. How successfully I've done that is up. you can decide, but it's a frog jumping, and it gets noisier and noisier and noisier until you can't even tell what's going on here, right? So now, what we do is when we train the model, we'll have our ground truth frames here. Okay, so basically we have our ground truth here, ground truth. We have our noisy images here, put noise. But what we do is we pass this in as a batch, all in one go, one sort of large, you know, vector into the neural network. And then what it's able to do is generate noise for every frame of what we need to take away from that image, from these images, to get that, right? So as I say, a video is a series of images. What noise we need to take away from our images in the video to get the original ground truth, right? And so you do that for all of the videos that you have in your data set. And I'm talking like hundreds of millions, right? It's many, many short clips of accurate descriptions. What you're able to do now is give your diffusion model pure noise, and then over a series of time steps, many, many time steps of let's say 20, it will then give you your frog jumping. It's getting very abstract, these images. So yeah, basically, and it works extremely similarly to how 2D diffusion works, where you start with noise and you ask it, okay, what noise do I need to take away from that? Do it again, do it again, do it again, do it again, and each time taking the noise away from those images and then passing them back in, and eventually you get a nice image of a frog jumping. And this is how, similarly to 2D image diffusion, it's able to start merging these abstract concepts. So, for example, a frog on stilts jumping while sort of lifting the stilts up or kicking the stilts out or something like that, right? It's able to learn the movement as well as what's in the frame, right? So, video done. Not quite.
Does it always use the same noise?
No, different noise. Different noise. And one thing that's important to remember as well, when you add the noise to each of these, it's unique noise per image. It's not the same noise for each image in your video. Otherwise, you'll get things like jitter and it won't work properly. So it's unique noise for all the images in your video, right? But what you do is you're passing it in as a batch. Let's think of this in terms of 3D, right? So let's say you have an image here, which is 720 by 1280, right? And you have this as a video. What you can think of is a video is many of these images stacked together, right, in slices. And what that makes is a cube. And let's say you have a video which VO3 would generate, which is 24 frames per second, and it does it over 8 seconds. So you have a cube with a dimension of 1280, 720 by 24 by 8, right? Or 24/8, right? And so let's work out how many pixels are in. I actually don't know this calculation, so I'm going to do it on the fly. That is 176 million pixels that these diffusion models need to diffuse over. And if you just use, let's say, the standard diffusion model that you're doing for 2D images, it's not happening. Even with the big servers at Google or OpenAI, they're going to really, it's not going to work, right? So we need a way of, firstly, condensing the problem space so that it's not going to just crash and run out of memory. But also, let's say at this frame here, let's say this is frame 150, you have let's say, and I'll go over this more, let's say you have someone kicking a ball at 150 frames, and at 0 frames the ball is rolling into the camera. How do we correlate that action is the consequence of something that happened here, right? Because these models have got to learn something called temporal consistency, which is, let's say, what happens at frame 1 will lead to something that happens down the line, right? And then it's able to interpolate between that. So, 2 problems. 1, how do we make it simpler? How do we condense all this data? And 2, how do we upgrade the network to then incorporate time, right? So let's go over how do we make things simpler. So there is a network architecture called an autoencoder. And I believe there's a video that's been done about this.
And you can use this for all kinds of things.
What they can do is they can condense images down into a latent space and then decode that image back to what it originally had. So let's say you have an image here of a frog again. And what you do is you'll have an encoder, which is just a series of layers which get smaller and smaller and smaller. And then that will condense this down into something called a latent space. I'll get over what that is in a second. And you've got a decoder which will take that latent space and go, I know what this was. This was a frog. And what happens is that the encoder gets very, very good at grouping concepts like the frog together in these values, which only the decoder can understand. We can't understand what these values are. So, for example, if you pass in an image of a frog, it will have a certain latent space. If you pass in another image of a frog, it will have quite a similar latent space, but then pass in an image of Saturn, it's going to have a completely different latent space. And what that does is it helps the decoder figure out what the original image was, right? But what's good about this latent space is that it's so much smaller and more condensed than your input image, right? Because it's more compressed. So you can actually think of these networks as almost like a compressor. And suddenly this latent space is so much more easy to work with, right? And so this brings me on to something called latent diffusion models, which essentially you'll have a noised up image here. And what you do is you pass it through an encoder. And this could be a pre-trained encoder as well. This could be one of the many available ones. And then what that does is it condenses it down into a latent space, and then you can use it on your diffusion model, right? Because the diffusion model doesn't care that this is latent space, right? It has no concept of what a real image should look like. You know, it's only us that interpret it as, oh, that's a frog. To the diffusion model, it's just a series of pixels. But rather than diffusing over pixels, we're now diffusing over latent space. And then when we're done with this, so we have let's say a diffusion model here, and we'll have caption of frog. Captions how we guide the network. And it will have a different sort of latent space. You update that many, many times. And when you're done with it, you pass it through, how do I draw this now? You pass it through the decoder, which will then give you your frog, like that. So with the latent space, what it does is it, inside of these values, you can think of it as almost like a graph, and values of a frog would be here. And if you put in an image of another frog, it will be close in proximity to each other. Let's say a fly would be kind of similar because frogs eat flies and stuff like that. But then Saturn, the planet, would be miles away, right? Because it's got no correlation. So the encoder is very good at grouping concepts together, and then the decoder will be able to take those values and then give you what the original image back. But that's not super important because, well, what we're interested in is this latent space here. The number of dimensions is much smaller compared to that, which means that when you use it on a diffusion network, the diffusion network does not care it's working in latent space. All it cares about is generating the correct latent space, the noise that when you take it away from the latent space will produce an image that when decoded will give you that, right? So that was with 2D, right? How do we do that with a video? So now we have a video here of a frog jumping, right? And this is the first frame, and we've drawn out the cube because we're saying it's a series of slices of videos, right? The problem is that passing this entire thing into an encoder doesn't really work. It's too large. It needs to be broken down, right? Now, what we do is convert this video into a series of patches. Now, how we create the patches is there's different ways of doing it. So one could be, let's say you just take parts of your frame, right? So you're just taking smaller parts of your frame, and you do this per frame. Or you could do it a different way, and the way I think is much cooler, which is you can take patches of space-time, i.e. you take a patch in one dimension and then you extend it, let's say 4 frames in the future. So what you then get is a cube of both space in your image and time. And just to be clear as well, I'm just going to put a frog jumping. And then each patch you pass into the encoder. And what we're going to do is we're going to choose patches of space-time. But there are different ways you can do these patches, right? So you then have these cubes here in latent space, which are much smaller than they would be if you're just doing it on these pixels, right? And then what you do is you then pass this into your diffusion model, right? And to be clear as well, apologies, I should have mentioned, this will be a noised up version of the video, as we said, how you train this stuff. And then the diffusion model spits out, I think that the noise you should subtract from these patches should look like this. And then what you do is you take this, apologies, add this caption in there. You take this, you subtract that from that, and then you get a series of denoised patches that then you pass into your decoder And then what that will give you is a final video of what you hope should be a frog jumping. You then can compare that to your ground truth and then update the diffusion model as you see fit. This is a complicated process, so this is a very high level overview. There are many different moving parts here, but that's essentially what you're doing is you convert them into patches and then you put them through the diffusion network. And you don't put them in individually. As I said, you're doing this as a batch of patches, but when you pass them into the encoder, you're doing it individually. And then it's almost like a jigsaw. You then put them back together. But what's important is that these patches are passed in the same order, because then that's how the diffusion network learns where patches should be in the video. So it breaks the problem down massively so that this network does not crash and have memory errors. And here as well, we've chosen to use patches of space-time, which is i.e. Patch of an image, but then it's images in the future as well. So this is how you try and reduce the complexity of the number of pixels it has to do. As I say, there's hundreds of millions, right? This, when it's working with the latent space, it's a lot less number of parameters, right? And you're relying then on the encoder and decoder network to sort of convert that back to pixel space. And these networks are very, very good, so you don't have to worry too much about them being efficient or not. So the other problem we have is that if we just use a 2D, a 2D UNet or whatever sort of architecture that they've used with 2D images, it's not going to work properly because it won't be able to associate that something that's happened way in the future is because of an action. So let's say that we have this frog here, and it's the frog jumping again, and we'll draw a little cloud as well. And we have a frame in the future. Let's say this is frame 150 of this frog jumping, right? If we just do 2D convolutions per frame, it won't be able to associate that the frog there is stationary, the frog there is jumping, but it's jumping because that frog was originally on the ground, right?
So the important thing there is that that's the same frog, I suppose.
Same frog there, and the only reason it's in the air is because it's jumped, right? So one way we can do that is using a transformer sort of approach with attention, right? And I believe there is a video on transformers, but we're not going to do this for LLMs. We're going to do this for video now. So like I said earlier, you have these patches of space-time, right? And so this is the frog jumping, okay? And I'm going to just do the frog on the ground. And then we'll just have like a rubbish purple one here of the cloud. So if you're familiar with a transformer, they use attention, which is essentially that you're able to focus, let's say on the frog jumping, and figure out what is associated with that frog jumping, right? So you can compare against the word jumping, right? And that will have a very strong connection, right? If you compare it against itself jumping, it has a very strong connection. The frog on the ground, it has a pretty strong connection because it's the frog on the ground, but then the cloud isn't any connection, right? A cloud isn't associated with the frog jumping. So let's say now we focus on this frog here. There is a pretty strong connection with the frog jumping. The frog is on the ground, so it doesn't have a strong connection with jumping at all, and then it has no connection with the cloud, right? But the point I'm trying to make with this is that by being able to compare directly against these patches throughout the whole video, it's able to associate concepts of jumping with the frog jumping in the future based on where it is now. That's how it creates this temporal consistency throughout the whole video, is based on comparing frames in the future with the past. If you just use 2D convolutions, it's not going to work properly. It's a very complicated concept, but essentially, you upgrade the neural network to compare across space-time. What I'm talking about is based on what they predict that Sora uses. Not VO3, not WAN 2.2, not even... So these models are getting even more crazy, right? So they're very, very complicated. And what I've tried to do is simplify this somewhat. But essentially, there's two things that they needed to solve to get video working. Is to reduce the complexity and to make these comparisons across space-time. And once they're able to do that, then you're able to get proper videos in there. Shall we have a look at some videos of what these models can do? So I've gone away and I've spent a little bit of money generating some videos using VO3, which is a state-of-the-art video generation model by Google DeepMind. And following on from Mike's video, I'm doing Frogs on Stilts, right?
Frogs on Stilts, the movie.
This is the movie, right? Part 1, 2, and 3 I'm going to show you. But basically I've set, the prompt is a bunch of frogs on stilts in a pond. They all jump up in the air and say, "We are frogs and we are free," right? So let's see what this looks like.
We are frogs and we are free!
The quality of this video is, you know, you can see the ripples, you know, spreading out. The frogs, they don't change color, they don't change shape throughout the whole video. They look like frogs. The quality is very good, very good. And VO3 is also able to do audio, which is a whole nother...
That's a different video.
A different video, yeah, for sure. Now, we've also got 2 frogs rapping.
That's not even a croak. I'm the top amphibian of this bog, while you are just...
You see how that's quite a complex prompt? Because I said a frog on stage with a gold chain, holding a microphone, having a rap battle against another frog at a music festival. And I've done one more video as well, which is going to show you how sometimes it can look a little bit weird, which was, I wanted a video of a frog where the camera zooms in on the frog and the frog goes, "Like and subscribe to Computerphile," right? And this is what we got in the end.
You must like this video and subscribe to Computerphile.
It didn't really understand how to say Computerphile, so it just sort of... They're getting really, really good. And we spoke about this in the MikeBot video, but when these models become so good that you can't even distinguish them from real life, what the hell's going to happen, right? There's going to be some issues with that, with disinformation and stuff like that. But hopefully, I've sort of explained how these models are an upgrade from the 2D diffusion ones and how we are able to get these really high fidelity videos.
You call that a rap, that's not even a croak. I'm the top amphibian of this bog, while you are just broke. You must like this video and subscribe to Computerphile.